as I alluded to in the previous video, we can use this distribution to find what fraction of molecules fits within a certain range of speeds, or even which are over a certain threshold, right, if we integrate out to infinity from a certain point. And to do that, we're going to take our equation that we have here, and we're going to integrate it, right? So we need to take the integral of this equation to figure out, what area lies within that. So let's do an example here. Let's say we have nitrogen molecules, and I pick nitrogen because that's what it's most of our atmosphere is made out of. And then we're going to say they're in air at 300 Kelvin, so just at room temperature. We'll assume that. And we want to know what fraction are traveling at speeds that are between 500 to 600 meters per second. By the way, that's really fast, and these particles around us are moving around at those speeds all the time. We'll see there's a pretty significant fraction in this range, but to a gas particle, that's perfectly normal, at least at room temperature. So things we need to know M. Well, for a nitrogen molecule, that's 28.014 grams per mole. We're going to want to switch this to kilograms per mole so that units cancel. So if we switch this to kilograms per mole, we get 0.028014 kilograms per mole. So we should divide by 1,000 to get to kilograms. So decimal place moves over 3 places. And we note the temperature is 300 Kelvin. We've already made that assumption. The other thing we need then is R, and in the right units. We'll want to pick joules per mole Kelvin so that everything's in SI units and everything will cancel out. Just as a reminder, a joule is equal to kilogram times meter squared over second squared. That's part of why we switched to kilograms per mole. The moles in the molar mass and the R constant are going to cancel out as well. So we should get something that is in terms of meters per second here once we have all the square roots taken care of. So R 8.3145 joules per mole Kelvin. Okay, so we've got everything that we need. So we need to integrate from 500 meters per second to 600 meters per second. And as long as we express everything else in terms of meters and not like nanometers or centimeters or inches or whatever, our units will all cancel out here. But that is something you always have to remember and worry about in physical chemistry. Okay, so then we have 4 pi times 0.028014 kilograms per mole divided by 2 times pi times 8.3145 joules per mole Kelvin times 300 Kelvin, all that raised to the 3/2 power, times u squared. This is our variable, so nothing we need to define there. And then we have our exponential term e to the minus 0.028014 kilograms per mole times u squared divided by 2 times 8.3145. I'll leave off the units because I'm running out of space here, times Kelvin. And just to double check our units here, right, joules, right, first of all, moles are going to cancel here, kelvins are going to cancel here. The kilograms will cancel within the joules. Kilogram times meter squared over second squared. All right, and so we should get something in meters seconds cubed over meters cubed, but that'll multiply by meters squared over seconds squared. Yeah, this works out. Okay. All right, and then there's du here. Okay, so we have all of this. Now you may be thinking, okay, how the heck am I going to solve this? And this is where we can use a computer to help us out. So I don't expect you to be able to necessarily do this by hand. You don't need to. So I'm pulling up a website that hopefully will become very useful to you. It's WolframAlpha. So this is a good website for doing mathematical operations. And this is based on Mathematica. You may have heard of that or possibly used it. This is the same company that makes that, has a web. It's not a web version of Mathematica, but it does a lot of similar things. So what we can do here is write out our equation. So integrate, and we'll integrate U from 500 to 600. Integrate U, we'll call it X. All right, got to come back to our equation here. All right, so 4 pi, integrate 4 times pi, thankfully Wolfram already knows what pi means, times 0.028014 divided by 2 divided by pi divided by 8.3145. There's extra 7 in there, divided by 300 raised to the 3 halves times exponential, oh, forgot the u squared. We'll call u x just for simplicity's sake here. X squared times exponential of negative 0.028014 times x squared divided by 2 divided by 8.3145 divided by 300, right? Yeah. All right, and we'll see if I type this all out correctly. From, integrate that equation from 500 to 600. All right, hit enter. All right, it didn't give me any errors, but this is not the answer that I had in my notes here. So let's see if I typed everything out. Oh, that should be a 2. That makes a big difference. Okay. There we go. That matches my notes now. Okay, so if we integrate this, we get a fraction, so 0.165. So we can come back here. And after all of that, all right, there we go. Equals 0.165, or we can say 16.5% of the N2 molecules lie within this velocity range from 500 to 600 meters per second. So hopefully that was useful as an example of how you can actually use this distribution, thinking about using the right units, how to type it into WolframAlpha, and get an actual answer at the end. You'll get a chance to practice with this as well in your homework.